Hey everyone. Hope everyone is doing well in these strange times, and I guess good evening if you're still listening in Europe, and good afternoon and good morning to where everyone else is. Today we'll talk about designing stateful apps for cloud and Kubernetes. State is hard. It is probably the hardest problem in distributed systems, right? And so with that, you always have to share a quote. So I'm going to share this quote that there are only two hard problems in distributed systems, exactly once delivery, guaranteed order messages, and exactly once delivery. hope folks get the joke. But let's talk about state a little bit. So what kind of state do you have? There's many different, and this doesn't come close to encapsulating state. So you have structured data, kind of like what you think of as traditional SQL-like tables, semi-structured logs, JSON. You have interesting new types of data, graph and networks, unstructured data, binary files. You have some configuration stuff, right? And we have increasingly, we have machine learning models, parameters. By the way, when I talk about ML, there are really two scenarios. One is when you're building the models and when you're serving them, which are kind of separate or different. So when you think about state, there's some characteristics that you want to think about. So is the state mutable or immutable? That makes a huge difference. In the case of things like models, they might be like immutable in the beginning and then immutable later when you serve them. What about its persistence characteristics? How temporary or permanent will this data be? How long does it have to live? When can you get rid of it? And you have the classic cap theorem issues. How available do you want it? How consistent do you want this data as you retrieve it from different points in a cloud? What is the latency like? So those are all things to think about when we think about state. So typically, how folks treat state is that you deploy your app to Kubernetes and you use it in what I call the stateless mode, which is that you punt the state to the database, right? So your application goes into containers and it can get restarted. So what that means is that you're going to put everything into different cloud services. So here, I think this is somewhat typical. You might be using multiple services. And so you can imagine that in your stateless app, you can imagine you're taking requests or you're executing different operations over time. And over time, you might be using different kinds of state in different ways. So you might be using your database with every operation or majority of them and different types of cloud providers at different times. A different way to think about state, which is useful, is to think about where it is. So you have your application in a container, you have memory, and you have your container image, which are read-only disk images, and you have a local disk which you can write to. However, these things are not persistent, right? So the memory of your application goes away when the application restarts, and your disk, what is written to your temporary local disk, goes away when the container restarts. So this is why the cloud storage and services are so important. That's where you have to persist things. And this has a lot of implications. But wait, I thought that stateless would solve all my problems, right? So here's some observations about stateless. It is a pattern that works for many, many scenarios. This is something that the majority of deployments in Kubernetes are like for this pattern, where your persistent state is pushed to other services. This, of course, has cost implications as the amount of state increases. then the cost of that goes up. Another implication is about latency. So where you keep your state determines how expensive it is to interact with it, to read or write it. So for persistence, this means that every state change can potentially involve the network. Another important implication is about recovery. Because the local state does not get persisted, when your container restarts, or even when you do upgrades, which is a really important scenario, most likely, instance 1 of your application will get restarted on a different host, right? So all your local state, you have to think about how to recover your local state or any state that you have from different sources. If you're using this paradigm where all of your state is pushed away, essentially that comes for free because like you can just get your state on the go from these cloud services. Many of these cloud services are cloud specific. Nowadays, migrating across clouds is a concern. So one thing that has to be kept in mind is about how to have abstractions that allow you to work across different clouds, right? And another thing is that as you work with more and more state, oftentimes we have to think about how to keep state consistent across the cluster, across these different services. So one thing that I want to point out, just to highlight these different terms, there are so many terms that are coming about. People talk about stateless. However, there is really some state in most stateless deployments that people who use containers think of stateless. There is still some memory and disk they can use. And what I want to emphasize is that when you talk about serverless, the big difference in these terms is that with serverless, you really do not have this memory and disk. And what I mean is that the state in a container, that can survive across invocations. It's just that it fails. It's just that it goes away during failures when you restart a container. However, for when you are deploying to service environment and you have functions as a service, you really have no idea where these functions, they can be running anywhere, right? So that means that you can't even use that memory and local disk state. This is the reason. This is the reason why in architecture, newer architectures coming out, such as cloud state, there was a lot of good talk earlier about that oftentimes you have to have a proxy or another way of keeping that state outside. So, so if you remember, we're talking about the stateless approach where we want to keep everything in the cloud. So, so after a while, you realize, okay, so I'm putting all my state off into the cloud. This starts to get the more and more expensive, the more data that I have. So as we deal with more and more data, one pattern that you can use to help with this is something called the local state pattern. And this is where it's a two-tiered approach, where I'm using temporary local storage to affect my communication patterns with my cloud storage a little bit. You'll notice that the arrow on the left are kind of like requests or events coming in. They're very small, so there's a lot of them that might be coming in. And what I'm doing with this local state is I might be able to batch my reads or writes, or I might be able to transform this into a different kind of state or delta state that I can read or write. This allows me to read or write more efficiently into storage. An example is that maybe I'm constructing small fragments of a file and then I push the whole file to S3, right? So this is a way of reducing costs and improving latency. And this is something that a lot of apps are doing. One effect of this pattern of using local state is that I have to deal with Affinity, because I might have to, as I build up my state, I might have to ensure that only requests or events of a certain kind come to a certain node. Another question is what happens when this goes away, right? So we know that this is not persistent. So this is something that has to be thought about, is that if I'm building up a file, for example, how do I recover the little pieces if something goes wrong? So this brings us to logs, the log pattern of dealing with state. So a log is a way of keeping track of individual events or mutations to my state. Right. So thinking about a log is really useful, because with the log, I'm able to reason about state changes. I can break down my changes over time into what are these dark gray colored boxes, which are the individual events. And then what you have with these pink points are called checkpoints. And what the checkpoints represent are snapshots in the state. So the checkpoint at op2 over there, I can see that my database is at a certain point. And what I can say is that in the case of failure, I can go back to that point in my state, and I can slowly build up my state again using the gray boxes. And what this pattern says is that I should be able to replay any sequence of events and build up my state gradually. And this gives me a way of basically getting to any point that I want in my state. It lets me look at state as essentially it's like a function that morphs over time, right? And this becomes the foundation of pretty much all modern databases and data systems, because in any failure, I'm able to go back and replay events and reconstruct state. An example of this is in FiloDB. We see these different patterns, the log pattern and using local state all together. In FiloDB, we use a column cache in memory, and we also have some local disk state as a Lucene database. And what happens is that we have a lot of really fine-grained time series events coming in through Kafka, and they get transformed through the column cache into bigger blobs. This reduces the writes from potentially millions of samples per second into thousands of much more coarse-grained writes. And what happens when a failure happens is that this state can be rebuilt from Kafka. We can go back and we can read from a checkpoint and rebuild the state. The only thing that's unfortunate about this pattern is that as your state grows, like if you're talking about tens of gigabytes or so, then recovery time gets slower and slower. And if we take this pattern and we think about it, the way that we think about it is that events are coming in, and you can think of your app as outputting data and outputting commands or state changes. So this pattern is very central to a lot of reactive paradigms, including event sourcing, CQRS, and the way that a lot of, for example, like frameworks in Akka works, is that we're talking about taking incoming events, transforming them, having an abstraction for dealing with handling state, such as an actor, for example, that can build up state, and then you can output this data. And this way you really have a really nice progression and control of state. And if there's a failure, you can roll back, and so this simplifies a lot of state handling. So now we've been talking about how to handle state in an offline way in the cloud. Let's shift to talking about what I call stateful Kubernetes, which is using patterns in Kubernetes for handling state, namely persistent volumes. So persistent volumes are a bit different from, so the typical container, like we said, if you write into the local disk, it gets thrown away. A persistent volume is basically another attached volume on your container, but it doesn't go away. So the memory, we know, will not persist if it restarts, but the persistent volume actually will persist across pod restarts. Persistent volumes use standard POSIX file semantics-ish for the most part. It basically appears to your application just like any other mount volume. And it can be configured using a YAML config where you configure what type of persistent volumes. And there's a couple of different types. The most basic kind is called the local persistent volume. It is basically a hard drive or SSD. But there are a lot of, there's two different other kinds that provide higher resilience, which is that there are networked and replicated services, which are not shared, which means that a single pod or single container will attach to one persistent volume. And every cloud provider has ones for this. And examples of this include the EBS and the PD on Google Cloud, and things such as Ceph and Scale.io. And depending on how you configure it, they can actually come pretty close to the local disk in terms of performance and latency. They are also less common, but they're also shared network storage services that you can attach to persistent volumes, including things such as Gluster and NFS, and the Elastic File System, EFS. So here's an example of a provisioning YAML, is that you would specify a provisioner which points to the type of storage that you want, and you can put in different parameters. Notice here for UBS, I can put in the IOPS per GB. So there's parameters that allow you to basically say how much, how fast. And the really neat thing is that I can decide on these characteristics at deploy time. So I basically, for the same application, I can deploy this to AWS, and I can use the same abstraction to deploy it to different cloud, and it basically just switch out my YAML. If you use persistent volumes, they should be used together with Kubernetes StatefulSets. So a typical Kubernetes deployment is where your pod can be deployed to any host, and when I restart it, it can come up with a different host, and it might be attached to a different disk, right? But a stateful set is a different paradigm of managing Kubernetes clusters, where your persistent volumes are essentially attached to your pods, and each pod actually has a number and has its own has its own IP address as well. So you get basically affinity, and if a pod was to go down, it would be restarted and would be sure to be attached to the same persistent volume it had before, which is how you get the cloud persistence. It ensures this connectivity. Stateful sets also changes the way that upgrades and shutdowns work. It changes the order, and it causes it's essentially does like one pod at a time, rolling upgrades. So why would you want to do something like this? Well, one reason might be that you want to run, pretty common is to run stateful services in a database yourself to save some money. But there are also a lot of scenarios where it's advantageous to have local state even for your application. For example, maybe you have a large amount of state, and you want to you want to improve on your latency and improve performance. So you might go with a local key value store instead of a cloud database. Another very common reason is for things like machine learning. For example, if I'm building a model, the model might take a long time to build, might take hours, and instead of copying files to an S3 when it's done, by taking advantage of persistent volume, I can actually ensure that this pretty much all my progress is saved as I'm building it. And there's other things like using Lucene. And this way you get one abstraction with local state that you can use on pretty much any cloud. So this is how a lot of people run. Probably a lot of people run into persistent volumes. Is you have your database, Postgres, MySQL, and so on, and you have a leader and follower, and you would use persistent volumes to ensure that during failure that they get restarted properly. With this scenario, you have multiple servers that you can have for queries. However, you need to set up replication and ensure that that network setup is okay. This pattern also works for other like NoSQL databases such as Cassandra, where you can have a stateful set for each set of replicas, and you would then ensure that each one gets separate attached disks.
Evan, we've got a question on the channel. Does GCP support shared persistent volumes between multiple pods?
Shared persistent volumes between multiple pods. I'm not sure about GCE. I know that AWS has at least 2 options for that. I'm not sure if GCE has that explicitly, but I believe that you can still use generic ones such as cluster of S. Okay, so let's keep going. So I just wanted to emphasize the difference between having a persistent volume versus, say, using an S3 and the 2-tiered local state approach, right? So basically on the right, we would be using local state to build up, say, a file and write to S3 or to transform the state. And in that model, what we find is that using Kafka and using the cloud services is very essential, and you have a lot, and it causes a lot of network overhead. And the reason is because in the case of failure, you need to read from Kafka, and you're also persisting data to cloud services all the time. On the left-hand side, you have the ability to reduce your Kafka clusters, the size of that, as it is no longer needed. The need for recovery for that is much less or reduced, and you have faster local state. But there's other kinds of trade-offs. So this is really interesting, is that oftentimes we think about different databases that everyone uses. You have like Mongo and Cassandra and so on. But when we think about the big data ecosystem, what we realize is that the foundation of much of the big data ecosystem in the last decade has been HDFS. It's basically, which came from the Google file system. Basically, the foundation is replicated, distributed, reliable storage. And what we noticed is that a lot of big data systems have been, Yarn, Spark, HBase, Storm, and so on. Like a lot of these things, they are all built on top of this file system. And what you see in the Hadoop ecosystem is that instead of basically every subsystem having its own way of distributing and coordinating, having its own coordination system, that they all reuse the same underlying mechanism, which is a really neat way of thinking about it, that it really is a pretty interesting building block. And just to explore this a little bit, and I realize this is probably very different from most reactive talks because I'm talking about local state, but let's say I have this replicated persistent volume. I can add things on top of it, such as RocksDB, Lucene, ML models, other things like that. And when I use that with a Kubernetes model, what I notice, what I would do is that you would attach a local PV to each pod. Typically, you do this. You can also do the shared thing, but that has different implications for your application. But let's say that you go with a local one for each pod, and so the implication of this is that one, you have to shard your app yourself, although you probably have to do this anyway. but then each one gets a consistent storage that works for different parts of your app. So this can be an advantage or disadvantage depending on how you look at it. But basically, you have one storage model that's shared for everything in the app that uses that. And you can then layer this, right? So how do I shard your state? So now let's bring it back to reactive technologies. You might use something like, Akka cluster that can shard your actors and can help shard your state and help route messages to different shards. And you can use event sourcing to, again, build up the state. So basically these technologies can all be complementary and add on top of one another. Right? Another different use case, this is taken from Amazon's website. They have something called FSX, which I hadn't heard of before, but this is more of a shared file system instead of individual persistent volumes. But something that you can do is you can run a big training job that writes files to this shared persistent volume. And then you can serve the resulting models on your containers. And so this is another model. I can see this working in a different way too, is that you can have individual containers that are running, say, Python jobs that are doing training and building local state, and you can copy those out and serve it. So that I see that happening more and more. Okay. So just to recap a bunch of things that we talk about. So I want to emphasize that the cloud data services and persistent volumes are not, they're not exclusive. In fact, you can use both and they can complement one another, and they have just different trade-offs. Where the cloud data services, you're talking about replication distribution being handled by those services, and you work with individual database APIs. And the persistent volumes, you have a very different style where the storage is handling the replication for you, but you handle more of the sharding logic yourself. And finally, just to conclude, think about where your state lives and how that interacts with your infrastructure and what are its characteristics. Think about how you recover state and how you handle failures, and the use of something like a log pattern for reasoning about state. And think about using things such as persistent volumes for advantage in your applications. Thank you very much. I think we're at 3 o'clock.